Oh, hi. I'm Alex McNabb. Today I'm going to talk to you about the Senior Design Project for ECE Group Number 2. Along with Nick Kniested and Matt Baumgartner, we are going to present our chainsaw sensor package.
Hi, I'm going to give you a brief overview of the chainsaw sensor package. The chainsaw sensor package is designed to sense a kickback. A kickback is when a chainsaw comes in contact with an object and kicks back rapidly toward the operator of the saw. If the blade is still rotating when it comes in contact with the operator, it can cause serious injury for obvious reasons. Our electrical system can sense the kickback by using accelerometers and gyros, process those accelerometer and gyro signals within 3 milliseconds, and send 5 volts out to say, hey, I saw a kickback, something needs to happen. Now, the mechanical engineering group designed a brake that can be actuated based on our 5 volt signal out. This is all so we can accomplish a safer chainsaw.
I am going to expand on the project overview and talk about the engineering requirements given to us by our sponsor, Wow International, and our mentor, Drew Arnold.
As you can see, these are engineering requirements. Our first requirement is to output a signal high, which is represented by 5 volts DC, if a kickback occurs. Otherwise, output 0 volts to represent a signal low. Our final design must be smaller than 6 inches by 8 inches by 3 inches and operate consistently at 100 degrees Fahrenheit and withstand forces up to 70 Gs. Our product must be powered by 36 volts DC and draw less than 50 milliamps. It also must react faster than 10 milliseconds. In fact, ours reacts within about 3 milliseconds. It also must recognize the difference between noise, which is about plus or minus 20 Gs, and kickback events up to 70 Gs. We also want to filter the noise to less than plus or minus 20 Gs, and retain over plus or minus 50 Gs for the kickback events. We also want to monitor at least 70 Gs in the X and Y axes. These are our desired features. We want our design to be implemented on a PCB, and it must monitor 360 degrees around the Z-axis using a gyroscope. And also we are to add X, Y, and Z values together and compare the result to sense a kickback.
This is our metal box, which we use to simulate the inside of the chainsaw. It meets our engineering requirement of being under 8 by 6 by 3 inches. If you take a look inside, you'll see that we implemented everything on a PCB. This was for ease and for better results from our sensors. We have here is an accelerometer monitoring the Y-axis. This is a gyroscope monitoring around the Z-axis, and another accelerometer monitoring the X-axis. These all are filtered actively through a low-pass filter of 200 hertz into a microcontroller, the Tiny26, and is outputting through the 0 and 5 volts to the chainsaw brake. Coming up, we will discuss the unique design considerations for our projects. You will hear us talk about the sensors, the filter, the microcontroller, and the physical package of the device. From this, we will also discuss the testing procedures and talk about the device that we built to simulate a kickback. This will all be discussed further in the block diagram section.
This is our top-level block diagram. From here, we will go into each individual subblock and discuss the implementation of each block. The chassis block will define the physical requirements of the final device. The device must be able to withstand several environmental stresses and fit within the chainsaw of size 6 by 8 by 3 inches. It will consist of 2 printed circuit boards at 90 degrees. The device must be able to handle heavy vibrations of plus or minus 70 Gs in all directions. To minimize movement of the device, screws will be attached from the holes to the inside of the chainsaw casing. The PCB must be able to consistently maintain shape and function between temperatures of 100 and 0 degrees Fahrenheit.
The power supply converts the 36 volts DC supplied by the chainsaw battery to the 5 volts needed for our system. This would leave 31 volts to be dissipated by the power supply. Multiplying by the maximum load estimated by our package of 50 milliamps amounts to 1.55 watts dissipated. Boasting a minimum efficiency of around 88%, the TPS 5410 switching voltage regulator was chosen to build a power supply around in order to improve battery life and efficiency of the system. With an 88% efficiency, a maximum of 186 milliwatts of power will be lost through heat.
The MEMS sensor is powered by a 5-volt DC signal from the power supply with less than a 10% voltage ripple. The external interface, environmental 1, is the acceleration resulting from the chainsaw. To sense the external interface, we use 2 accelerometers and 1 gyroscope. All MEMS sensors output an analog signal sitting at 2.5 volts, representing 0 Gs. The output then swings from 0 to 5 volts. These sensors were chosen by our sponsor, Blount International.
The purpose of the conditioning block is to provide necessary filtering and bandwidth correction to the output of the MEMS sensors. The unfiltered signal will contain information about a kickback and operating noise. This signal needs to be filtered so that the microcontroller will receive a signal that is free of operating noise. An active low-pass filter of 200 Hz was chosen to pass any kickback signal to the microcontroller.
The microcontroller is powered by a 5-volt DC signal. The input is from the low-pass filters, and the downloaded code is the code used to program the controller. Lastly, the output of the controller is 5 volts DC after a kickback occurs, and is 0 volts otherwise. We chose the Tiny26 for our 8-bit controller because it has an internal analog to digital converter, met our size requirement, and is onboard programmable. We also already had the tools needed to program the device.
Program code for the Atmel Tiny26 was written in C and compiled via the Universal GUI app, then converted into a programmable hex file. The code activates the onboard analog to digital converter on the microcontroller and samples the filtered output for all 3 sensors. This digital number is then conditionally acted upon by the controller and, depending on its intensity, is labeled as a kickback by the microcontroller. If the proper intensity is reached, 5 volts will be output by the controller to indicate a kickback event.
Okay, unpowered, we're sitting here at 0. Coming over to the lab supply. Click it on. The testing apparatus. We got the package on there. Powered on. We're sitting at 2.5 volts as our DC offset. That's from the accelerometers, and then we also have a G's up here. Okay. Okay. Wait. Go for it. Five volts. Things back.
Welcome to the reaction time test. I'm going to beat this on the table, and then we'll see a trigger on the oscilloscope. Or not. What's our delay?
You can reset it and try again.
Okay.
So that's on the gyro, rotating around the Z-axis.
So Nick, now that you're finished with senior design, is there anything that you can offer our next year seniors as advice?
Well, one piece of advice I give is to begin actual work on your blocks fall term. Keep in mind they're not due until winter term, but any progress you can make fall term will greatly help you in the middle of winter term. Another piece of advice I give is to keep your requirements simple and feasible. Keep in mind you can change hard requirements after the fact, but it's very difficult to do and you must get mentor approval, so design them feasible to begin with.
This concludes our presentation for the chainsaw sensor package. We would like to give special thanks to Donald here for his help, for our mentor, Drew Arnold, and for our sponsor, Blount International. We'd also like to thank you for watching our presentation.